Okay, so here's the problem. We want to find the area of the region in the first quadrant bounded by the curves y equals 4x, y equals 5 minus x over x, and y equals 0. And this is just the x-axis. So we'll provide two solutions, one using vertical rectangles, the other using horizontal rectangles, and you will see that there is in this case one solution which is better than the other. So let's start with first sketching the region as always, and we'll first find our points of intersection. So y equals 4x, y equals 5 minus x over x. Let's see where these two curves intersect. So we'll equate the y's. So 4x equals 5 minus x over x. You can multiply across by x, and you'll have that 4x squared is equal to 5 minus x. And if you send everything on the left, you'll have a quadratic polynomial, and you're going to try and find the roots of it. And here it may not be easy to see how we can factor this by inspection, so you can fall back on the quadratic formula. So the solutions will be minus b, so negative 1, plus or minus the square root of b squared, which is 1, minus 4ac, so minus 4 times 4 is negative 16, times negative 5 is positive 80 over 2a, 2 times 4, 8. Now we can simplify this to the root of 81, which is 9. So we get negative 1 plus or minus 9 over 8. So if you take the negative sign, you'll get negative 10 over 8. If you take the positive sign, you'll get negative 1 plus 9, 8 over 8, which is 1. But notice that we are talking about a region in the first quadrant. Therefore, x and y are both positive. So we have to reject this solution as it is negative, and we're left with just one positive solution, x being 1. Well, we want the point of intersection, so we need the y-coordinate. So we have x equals 1. And if x is 1, y is 4 times 1, which is 4. So we have one point of intersection, 1, 4. And we can see if these two curves also intercept with y equals 0, the x-axis. Well, clearly, y is 0 here when x is 0. So we have the origin, 0, 0. This is pretty trivial. And what about this curve? Where is this equal to 0? Well, as it is a fraction, it can only be 0 if the numerator is 0, and clearly 5 minus x is 0 if x equals 5. So we have the point x equals 5, y equals 0. This is the 0 of 4x, this is the 0 of 5 minus x over x, and this is the point of intersection between our line and this curve. So now we can sketch the region. And you can rewrite this function so as to make the sketch more apparent. If you think of it, you have y equals 5 minus x over x, but if you divide across by x both terms, you'll have 5 over x, which is simply the function 1 over x but multiplied by 5, so it's going to be a little higher, minus x over x, which is 1. So think of it this way, this is just 1 over x, but a little higher as it's 5 times bigger. The minus 1 gives you a vertical translation by 1 down. So we have a fairly simple set of functions to graph. This is the first one, y equals 4x, and the x-axis y equals 0. So let's sketch the region now. So let's sketch this function first. So we're going to sketch 1 over x. It looks a little higher, and we know that this function is 0 when x equals 5. So it's going to look something like this. and this is the point x equals 5, and this is our function y equals 5 minus x over x, or again if you prefer 5 over x minus 1, same thing. And now the other curve is very trivial, y equals 4x, so it goes through the origin, so there you have it, so y equals 4x. So this is the origin, this point of intersection, this is the 0 of this function, and of course where our curve and y equals 4x meet is the point 1, 4. So x equals 1 and y equals 4. And now we can clearly see the region, right? In the first quadrant, y equals 4x, y equals 5 minus x over x, and y equals 0 bound this region. And now we're looking for the area of this region. So let's first be naive about this. Everything is given as y equals a function of x, so let's go with vertical rectangles. But there is a bit of a catch if you think about it. If you draw a vertical rectangle, say between 0 and 1, then its position is x. The width, of course, is dx, as the width is a small change along the x-axis. And you see the height of the rectangle is 4x. It's the y value on this curve. But if you draw a rectangle between 1 and 5, say here, again the position is at x, but now the height of the rectangle is no longer the y value on the line, but the y value on this other function. So we'll have different expressions depending on if we are between 0 and 1 and 1 and 5. This will mean we'll have two different integrals. Okay, well we committed to vertical rectangles, so let's bite the bullet. Let's see what comes out of this. So, between 0 and 1 again, our rectangle, the width is dx, small change in x, and the height going from y equals 0 to y equals 4x is simply 4x. So the area of a rectangle between 0 and 1 is the height of the rectangle, 4x, times the width, dx, and that is just the height of one rectangle. If you want the total area between x equals 0 and x equals 1, you need to add the area of all the rectangles over this interval. And we know that since dx is an infinitesimal change in x, it means that our rectangles have a width shrinking to 0, so this will give us the exact area. But this is again the area of just one rectangle. To get the total area of this region, we have to sum the area of all the rectangles, again with respect to x, and this part of the region spans from x equals 0 to x equals 1. Okay, that's only part of the region. To get the total area, we have to add now the area of the other region. So here, well, the height of the rectangle is the y value on the other function, which is 5 over x minus 1, and I'm going to use this as it will be easier to integrate. This is the height of the rectangle times the width again, which is dx. This is the area of just one rectangle. To get the total area of this region, we have to sum all of the areas of the rectangles as x ranges from 1 to 5. So we sum the area of our rectangles as x goes from 1 to 5. And now from this we get the total area of our region. Okay, so now we're good to go. Let's evaluate both integrals, and let's see what the area of this region is equal to. The point is, because we used vertical rectangles, and the curves on top were changing at some point inside of our interval, we had to come up with two different integrals, which is kind of annoying. But let's see what comes out now. So let's use, on both cases, the fundamental theorem of calculus. Let's first find an antiderivative. For x squared over 2 is our antiderivative. And we evaluate this from 0 to 1. Plus, same thing here, antiderivative, so 5 over x integrates to 5 ln of x, minus 1 integrates to x, and we evaluate from 1 to 5. Well, here we can simplify a little bit, as 4 over 2 is just 2. So we simply have 2x squared. So we evaluate this function at 1, we get 2 times 1 squared is 2, minus the function at x equals 0, but 2 times 0 squared is 0. So all we get from this is 2, plus this expression. So we evaluate this at x equals 5, we get 5 ln of 5 minus 5. I can drop the absolute value as 5 is positive, then minus this expression at x equals 1, but ln of 1 is 0, so this goes away, and we're left with minus 1. So in the end, what are we left with? Well, we have a 5 ln of 5, and if we look at the constant terms, we have 2 minus 5 negative 3, plus 1 negative 2. And so we're done. The exact area of this region, bounded by the curves y equals 4x, y equals 5 minus x over x, and y equals 0, is 5 ln of 5 minus 2. If you want to get a feeling for a numerical value, you can use your calculator, and you will find this is approximately 6.047. Okay, so it wasn't too bad, but what was unfortunate is we had to come up with two different integrals for the area of the region. Let's see now if we used a horizontal rectangle, if we get a better solution. So let me just sketch the region over again quickly. Okay, so now we have a region, and if you see, the reason why with vertical rectangles it wasn't such a good idea is the height was given by the curve being on top of our interval. As we go from 0 to 1 and 1 to 5, the curve on top changes from y equals 4x to y equals 5 over x minus 1. Now what's interesting is if we go with a horizontal rectangle, then the height will be the length of the rectangle, and will be the x value on the right minus the x value on the left. What's interesting now is the curve on the right is always going to be the same, this one, and the curve on the left of our rectangle is always going to be the same. So using here a horizontal rectangle will give us the area from a single integral. And this is what you should have noticed right from the beginning. So again, I've shown you vertical rectangles just to show you how, in a sense, unfortunate it is, and to see that we will get something nicer with a horizontal rectangle, as we will not have to break down the area into a sum of two definite integrals. So let's see how this works out. So we draw our horizontal rectangle. Now the width is a small change in the y direction, therefore it is dy. And we want the length of the rectangle, which is again a segment along the x-axis. So we need to find the bigger x value, minus the smaller x value will give us the length of this segment, therefore the height of our rectangle. Well, we're asking in both cases what is x at the endpoints. Well, let's see. And again, because we have a dy, everything we measure must be a function of y. Well, if y equals 4x, x is simply y over 4. Or if you prefer, a quarter y. So on this point, we are on this curve. At this point, x is 1/4 y. Now what about this point? We're looking for the x value when we're on this curve. Well, let's solve for x as a function of y in this equation. Let's do it here. So if I add 1 on both sides, I'll get y plus 1 equals 5 over x. Send x up here, send the y plus 1 on the bottom, and you're left with x being 5 over y plus 1. So when we're looking at the right-hand point of our rectangle, we are on this curve, and on this curve, x is 5 over y plus 1. And now we can find the height of our rectangle quite easily. As we've said, the height is just the length of the segment. This is a segment along the x-axis, so the length will be the bigger x value, 5 over y plus 1, minus the smaller x value, 1/4 y. And now we're good to go. We have the length of our rectangle, or the height, times dy will give us the area of one rectangle. Height times the width, so we have the area of our rectangle. And of course, to get the total area of the region, we have to sum the area of all of our rectangles. And here again, be careful, we won't sum from 0 to 5. We are summing, if you look at the position of your rectangle, it is positioned along the y-axis. So we are summing with respect to y. And so along the y-axis, our rectangles begin when y is 0. And we go all the way up until y is 4. And this will give us the exact area of our region. As we're adding up all of our horizontal rectangles from y equals 0 to y equals 4. And if you notice, using now horizontal rectangles, we have a single integral. So let's see if we get the same answer. Hopefully we do, as we are yet again finding the area of the same region. So, find an antiderivative. The integral of 5 over y plus 1 is 5 ln of y plus 1 in absolute value, minus 1/4 y squared over 2, but 2 times 4 is 8, so it's minus 1 over 8y squared, or if you prefer, y squared over 8. This is our antiderivative, and now we must evaluate, by the fundamental theorem of calculus, this function between 0 and 4. So let's see what comes out. Replacing y by 4, we get 5. Ln of 4 plus 1 is 5, so 5 ln of 5. Minus 4 squared is 16. 16 over 8 is 2, so minus 2. Minus this function when y is 0, but we get here ln of 1. Ln of 1 is 0, so this term goes away. Minus 0 squared over 8 is also 0, so this function evaluates to 0 when y is 0. So there's nothing left. And so the answer is 5 ln of 5 over minus 2, as was in the case of vertical rectangles. And again, this is approximately 6.04 0.47. And this was more elegant than our previous solution with vertical rectangles. So what's the lesson here? Sure, we worked out the area to be 5 ln of 5 minus 2 in both cases using vertical and horizontal rectangles, but we should have done this right from the beginning, because we noticed that as we went with vertical rectangles, the height was the curve on top, and as there was a change on which curve was on top between 0, 1 and 1, 5, we should have known that this would have given us two different integrals. Whereas with a horizontal rectangle, the length of the rectangle is always right minus left, and the curve on the right is always the same, the curve on the left is always the same, and this tells you that you will be able to find the area of this region using a single definite integral. So always take a few seconds to really think this over, see if you're better off with horizontal rectangles or vertical rectangles. In this case, we were better off with a set of horizontal rectangles. And that's it.